Assalamualaikum warahmatullahi wabarakatuh and very good morning. Today we are going to present about analysis on bracket. We have been given task for this semester is to do the project within 4 groups of members to do this project. First of all, I want to introduce our group member, which is we are from team member group 1 and our leader is Abdul Mohaimin and the fellow member is Fahmi Yasir, which is me, Adik Koyum and Ahmad Samuel. The introduction about this project, analysis on the bracket. Sheet metal filling cabinet have grown increasingly prevalent in office as civilization has progressed. The failure of the tiny bracket below causes the interlayer sling to fail when file cabinets store too many paper documents. The theoretical and finite element method were used to investigate the stress and deformation of bracket. The result revealed that minor machining shape flaw has no impact on bracket mechanical behavior. The failure of small brackets is due to their instability rather than their strength. Brackets have a number of advantages, including being inexpensive, lightweight, and durable. Metal brackets are often made from cold rolled steel that have undergone a through, through the processing procedure. Because steel brackets come in variety of size and shape, sheet metal brackets are widely employed in a variety of applications. However, if the load exceeds the bracket capacity, it may fail. This is our problem statement about this project. As we can see, as we mentioned before, brackets have been used for various ways in whole of load. As example, a horizontal force is applied at the center of the upper hole of the bracket and the bottom hole of bracket are fixed to the ground as in figure below. A lot of brackets have been filled down because they're getting load where it exceeds the maximum force of the bracket. So in this project, we are going to use CAD software, which is SolidWorks and FEMAP, to create a bracket model. And by use a proper modeling technique, a load application method and the displacement boundary condition will be approximate. So let's get started. So this is our geometry about our bracket. So this geometry is follow the requirement as stated in our project guideline. So this is material property. So young modulus is 206.8 gigapascal and the Poisson ratio is 0.29 and our the density of the bracket is 7,820 kilogram per meter cube and the thickness is 3 millimeters. So this is our how we apply boundary condition throughout the SolidWorks and the step by step. So the first step is apply at the center upper hole of the bracket. So there's a picture given to visualize how this step is going. Okay. So the second step is the material of bracket property defined as shown. So this one is shown. We put the material as stated in the guideline. So the third step is the bracket is meshed based on solid geometry. So this one is, as we can see, there's a lot of mesh in here. So the fourth step is rigid element. So that the element, as we can see from the picture here, was formed by connecting knot around hole with center knot of the hole. Okay. So the fifth step is 15,000 load is set at the upper hole of bracket, which is at knot of the center hole. So as we can see, there's a force, or we can call it load, on the center of the knot. So the fixed constraint will apply to the two bottom holes. So there's a two in our bracket. There's a hole at the upper and a hole at the bottom. So there's two hole at the bottom part. So we fix that. So this is our B1 modification, which will be explained by me. So B1 modification, we had about 6 modifications. So the first is B1, which is a 50 size millimeter to the bracket. So this one is B1 here. So this is our geometry. Our this is our major dimension about the geometry. So this is how we do the dimension in the SolidWorks. Okay, so this is our mesh geometry, the mesh view. So mesh property view. So, this is how when the load is applied. So as we can see, there's a bending here. But we can that this one is more detailed where we can see the where is the like the plate and the where is the place in that bracket have been exceed the limit of the property. Yes. So this one is number of elements 5,987. So the mass is about 0.661,033 kilogram. So this is like range. Okay, a range stress for stress and displacement. So this one is maximum stress, tension. About yeah, as you can see here, tension and compression. So this one is maximum displacement in positive direction and negative direction. Okay, so this one is B1 modification. Okay, so this is B2 modification actually. So this one is B3. So that's all from me. That's all from me about, so I will pass this presenter to the next speaker.
For this one, we changed the value of B1 from 55 mm to 60 mm. So as we can see, there is two picture. From the left side is major dimension, which is we sketch with using SolidWorks, and the right side is isometric view. Next, the figure from the left side shown mesh property 1, which is undeformed element, while for the right side, which is mesh property 2, deformed element. So this is mesh property 3 figures, deformed element, and we can see the output result from the table, which is we got maximum stress for tension and compression, and maximum displacement for positive direction and negative direction. And also we have number of elements, which is 6,556, and the maximum stress for tension is 332.28 megapascal, while the compression is 332.76 megapascal.
Hello and Assalamualaikum warahmatullahi wabarakatuh. I'm gonna explain the modification for 65 mm for my bracket. My modification, which is we can see here, is my dimension, major dimension, which is we change the middle hole at the center and the center of lower hole, which is 65 mm. Next is my major dimension here in 3D. So we can see here a different from previous modification. The middle hole is more higher than before. So next you can see that my modification bracket in mesh, we can see all the elements and the applied force which is our load at the center whole rigid element at the upper bracket, and our constraint force here is at on surface lower hole bracket on the both hole at the lower of bracket. So here we can see next is our mesh bracket, which in deform. We can see the bracket deformed to positive x direction because our force is in the positive x direction, and the constant force at the lower hole, they stay at its place and have a little displacement. So here we can see at the contour picture, the bracket is happen stress the stress happen at the left side as the high stress, and the right side also, which is near to the lower hole. So here we can see from the result the elements we get for 65 mm modification, that is 6,479 elements, and it weighs on 0.36433 kilogram. Next, for the maximum stress, because we can see here the tension is 346.51 megapascal. From the bracket, we can see the tension happen at the left side, as it shows a pattern of tension side. So while the compression is 335.54 megapascal, it shows at the right side, which is we can see it happens here is a compression stress. Same goes to our hole, our lower hole here. The left side is tension stress, and the right side is compression stress. So next is maximum displacement. As we can see, the maximum displacement happen here, positive direction is 0.00333530, right? And the negative direction is 0.00335114, right? So that's for B1 modification 65 mm.
Next is B1 modification for 70 mm. So here at the same place also at the middle hole, we lift up the hole higher, which is near to the upper hole. And here is my major dimension, and here is 3D modeling of my bracket. So next we go to the mesh element. We also same here, we apply same load 15,000 Newton on the x direction, and also at the same constraint force, which is on surface lower hole of both lower hole of the bracket. Next we jump to our deformed bracket, which is we can see here the bracket is turned to right also, which is on the direction of 15,000 Newton, and the difference between 65 modification and 70 millimeter for the modification here, the stress happen on the tension and compression is more higher. This is because the hole is near to the load 15,000 Newton, which give the tension is higher at 335.43 megapascal, and for compression is 341.73 megapascal. This modification will give you element 6,416 elements with a weight of 0.36433 kilogram. And it happens for the displacement happen here is 0.003352, right? And the negative direction for displacement is 0.00333343, right? So that's all for the B1 modification 70 mm. Thank you.
So next we go to B1 modification equal to 75 mm. So the change we can see on the B1 dimension, and also the length from top circle and also the bottom circle, because the line is in tangential. So the others are still the same, and this will be the shape in 3 dimensions. So for stress analysis, we use FIMAP, and it's just the same as before. We fix the both hole at the bottom, and also we put 15,000 Newton at the center of top hole to the right. And the stress analysis in terms of nodes and elements. So this is the deformation shape after the force is applied. So from the result, we get the maximum stress in tension 422.617 megapascal, and for compression we get 423.32 megapascal. While for maximum displacement, we get positive and negative direction 0.003479 radian. So for the mass, we get 0.35506 kilogram, and total number of elements for the analysis is 7,050. So the highest stress we can see from the picture is near to the hole at the bottom. So next, for optimum design, we use the B2 and B3 from the question as by using the lower bound, which is 9, and also for B4 and B5 we use the upper bound value, which is 30, so we get here 60. So from that we just use the try and error test to get the stress that near to 800 megapascal but still below than 800 megapascal. So we do two boundary conditions which are 110 megapascal 110 millimeter and also 105 millimeter. So we know that the 800 megapascal is between that range, so we just decrease and increase the value of B1, so we get the value of 108.6 mm. So this is the shape after deformation. The force applied and also the fixed point are still the same, so this will be the deformation shape after the force is applied. So the maximum stress in tension we get 789.195 megapascal. For compression we get 790.506 megapascal, while for and also for maximum displacement, for positive direction we get 0.0017786 radian, and also negative in negative direction we get 0.001778785 radian. So this is the lowest mass, which is 0.282213 kilogram, and also the number of elements are 3173. So the highest stress is near to this side, to the holes, bottom, both bottom side, and also near to the top triangle hole.
For discussion, we changed slot height of B1 to conduct a parametric study. So the purpose of the model is to analyze the deformed geometry, mass and maximum stress plot of the bracket with various B1 dimension. So the dimension of B1 is calculated with FIMAP, and the results are shown in table below. B1 configuration, we have 55 mm, 60 mm, 65 mm, 70 mm and 75 mm. And we got the maximum plot stress, mass model, maximum displacement, number of elements. As a result, for B1 of 55 mm, we got maximum plotted stress of 329.5 megapascal and a mass of 0.36103 kilogram. Beside that, the maximum plotted stress is increasing even though the dimension of B1 changed to 60 mm and 65 mm. So the maximum plotted stress for the height of 60 mm and 65 mm was 332.28 megapascal and 346.51 megapascal respectively, while the mass model had the same value of 0.36433 kilogram. Furthermore, when slot of B1 changed to 70 mm, the maximum plotted stress was 335.43 megapascal. The stress was reduced compared to slot height of 65 mm. Lastly, the maximum plotted stress increased to 422.62, while the mass decreased to 0.35506 kg when the slot height of bracket model B1 changed to 75 mm. In conclusion, the main of the project is to analyze of the bracket model in order to determine the ideal weight based on its geometry design and the force acting on the bracket using the properties provided, which include Young modulus, Poisson ratio, density, and the thickness, and constant force reaction on x direction, which is 50,000 Newton at the upper hole of the bracket. Finally, we can conclude the study case goal was accomplished because the project goals were met as a result of the findings. So SolidWorks and FreeMap are primarily used in this project to analyze geometry design based on the axial force acting on the bracket. That's all from me. Thank you.